Okay, so today we switch from the cross-sectional world to the space and time world. And it takes a little bit of a kind of a mind warp to think about panel data from a spatial perspective, because the traditional setup is very much with time series in mind. And so what I'm going to do today is a lot of background, actually, is kind of set the stage of what is the data structure used in spatial panel data, and how does that translate into the traditional model specifications of fixed effects and random effects in panel data, which you may be familiar with. And then I'll talk a little bit about dynamic panels, panel data where the observations at different points in time are incorporated. But that's pretty much the only discussion of that. And then we go back to what is called static panels. So these are panel data set where the data pertain to the same time period. And there is serial correlation between time periods, but not by the dependent variables or explanatory variables. And so then to close today and to kind of set the stage for Monday, where we look at the traditional fixed and random effects in more detail, we start by doing some pooled modeling. Pooled spatial models are very straightforward generalizations of the cross-sectional setup and can be relatively straightforwardly estimated with GeoDa and GeoDa space. So if I have time, I'll go over that as well. Today, so the reading is mostly, there's a survey chapter that looks at these different specifications, and then there's a technical discussion of spatial panels in chapter 10 of the 1988 book, but that's very technical. And then I developed two new documents that kind of walk you through setting up space-time regression in GeoDa and then estimating them with GeoDa and GeoDa space. So that's a little known feature in GeoDa, is that you can actually convert cross-sectional data sets that have data for different points in time to an actual space-time data set in the format that is typically taken by panel data software like software in Stata or in R, SPLM, or PLM require the data in a particular format. So GeoDa can actually can transform the data into that format. And then it doesn't, as yet, have specific panel data functionality, but you can estimate the pooled models. It's as a very straightforward, generalization of the cross-sectional setup. So let's first go over some terminology and some thinking about how the data are actually set up in a panel data model, the data structures, which is, it's important that you have a good mindset for that, because it is, the notation gets very complicated, I have to warn you. There's lots of Kronecker products. If you don't know what that is, I'll explain in a minute, but so it gets really heavy, and it's kind of important that you see what's going on in the different parts. So in the traditional setup, pooled cross-section time series data or panel data have observations that are indexed both by a location, or in standard microeconometrics that would be an individual, and as well as by a time index. So we use I for the cross-sectional index, and I goes from 1 to n, and then we use T for the time index, and T goes from 1 to capital T. So those are the two dimensions. So think of, say, different counties at multiple points in time, or individuals at multiple points in time, or house sales transactions at multiple points in time. So the traditional setup, as I mentioned earlier, is to focus on the time dimension. And in essence, the data are organized as n little time series. So if you think of the time series as pertaining to one observation, an individual or an observation in space, which is tagged by I, then we have period 1, 2, 3, 4, whatever, right? And for each I, we have a little time series like that. That's the way it's typically set up in panel data econometrics. Typically, the time series are short. So these are the kind of panel that you have in longitudinal studies where you follow an individual over time, or in census data where you have census tracts over time or counties over time, that kind of a setup. So when the time series are short, the focus, the interest tends to be on heterogeneity, and particularly heterogeneity of the unobserved kind. So if there are some unobserved effects that we have in the individuals, how can we take that into account in the estimation of the model? How can we properly take that into account? So as the time series get longer, then the focus switches to the time dynamics. And then typically, say a lot of international trade models are like that. You have a number of countries, typically not very many, 130, 150 at most. And then you have time series of annual data for 30, 40, 50 years, right? So then the two get more balanced, and then it's possible to use the time dimension to extract the spatial correlation, so to speak. Because then the spatial correlation simply becomes a bivariate correlation between two time series. And of course, things get complicated when you bring in heterogeneity. So for now, we won't talk about that, but just running ahead, think about everything that can change. It's not just the cross-section, where you could have dependence across the cross-section or heterogeneity across the cross-section. Now you also have that across the time dimension. So you can have all possible combinations of heterogeneity and time dependence. And from a theoretical point of view, it's really very important to think about which dimension dominates and which dimension goes to the limit asymptotically for the theoretical properties. So is the cross-sectional dimension dominant, or is the time series dimension dominant? Or are they somewhat balanced, which is a whole other area which is very tricky. So that's a traditional setup. The way we set up the data is, as I mentioned, as these short time series. So typically we have a given I, and then we rotate through the different t's. So if you think of this as a double loop in programming terms, we have I goes from 1 to n, and then within that, t goes from 1 to t. So we do I1, T1, T2, 3T, up to TT here. And then we go to I2, do the same thing, and finally IN, and do the same thing. So that's the way it's stacked. The reason I mention this is that all the textbook notation builds on this stacking of the data. So it assumes that the data are organized like that. So of course, they're not really stacked like this. It's vertical, right? So all the observations are organized. First index is the location, then we have all the time periods, then second location, all the time periods. Okay, so that's the classic textbook panel data structure that all the notation is geared at. And this notation, if you've taken a course in panel data, it gets really unwieldy very quickly because of all the, demeaning and other tricks that you use to get rid of these individual effects. Now, the spatial approach flips this around in essence. So I like to describe it as cross-sectional slices at multiple points in time. So the data will be organized differently as well, because we have the first cross-sectional slice, then the second cross-sectional slice, and so on. And with this kind of setup, it's really depends on the relative magnitude of n and t, what the interest will be and what you can do, basically. So if you have large n relative to the time period, you can focus on the spatial specifications. If you have small n and large t, which we just discussed, then you focus on the time specifications. Spatial is a side effect. If you have large n and large t, then you can do all kinds of stuff, but there's a danger there, and the danger is that you get carried away and write down specifications that in fact cannot be identified. The parameters are so convoluted between the spatial effects and the time effects that you can't figure out which is which and what is the actual space-time effect. So that's important there. And then of course, we stack the data differently. And this will matter once we move to matrix notation to remember which is which, right? So whereas in the traditional case, you start with the first I and then do all the T's, here you start with the first T and do all the I's. So the sequencing is different. So we go from I1 to IN for time 1, then for I1 through IN for time 2, and so forth. So then the stacking, I mean, obviously they're the same observations, but you organize them differently. So you can think of them as cross-sectional vectors stacked on top of each other. So in terms of a loop, the outer loop is T is 1, and then goes to T. The inner loop is the cross-section, is the I, and I goes from 1 to N, right? So just keep that in mind, because at the end of the day, they're just vectors and matrices, and you have to extract the different parts of them to figure out what are, for example, the individual effects if you look at heterogeneity. So then a typical data set looks like this. This is something that GeoDa produces. So it creates an overall tag number. This is necessary to keep the weights coordinated. Then it has a cross-sectional ID, and you see here a cross-sectional ID and a time ID. And in this example, the cross-sectional ID is a county ID. You see them changing. The time ID does not change. So, you know, T is 1 and all the cross-sectional units, right? And then we also have time-fixed effects, which GeoDa creates, and then the stacked variables. So this is one big matrix. That's the way to think about it. And so now the trick is, how do we get the right pieces out of this matrix when we're going to do things like take out the mean effect, which is a typical approach in panel data. You know, if you have individual effects that are constant over time, if you take the observations as the deviations from the mean over time, you wipe them out. You know, that's a classic trick. But how to write that in matrix notation is going to look very different from the classic panel data textbook case. And it's all because of the way the data are organized. So why do we organize the data this way? Because of the spatial weights. The spatial weights apply to the cross-section. And so if you mix the cross-sections, you know, as, you know, you have a little time series, then, you know, you cannot apply the weights as such to that little time series. You would have to reorganize the weights totally to do that, whereas now it's a very simple extension, if you wish, of the cross-sectional approach, where you have a spatial weights matrix for each cross-section. So that's why the data are stacked in this fashion and not in the traditional panel data setup. Then a couple more concepts before we look at some of the specifications. This one is very important because it comes back to bite you in several in empirical applications. So it's a difference between a balanced panel and an unbalanced panel. And basically, a balanced panel is the same cross-sectional frame over time. It does not change. So if you look at a city and you look at the neighborhoods in a city over different time periods, as long as the neighborhoods don't change, this is a balanced panel, right? There's actually, this is much easier to say than to implement in practice because, as some of you might know, the census tracts do change over time, especially if you look at longer periods of time. The counties also change over time, especially if you look at longer periods of time. So then you get into situations where you have to make sure, because the emphasis is on the spatial effects, you have to make sure that these spatial units are all compatible. And some companies like GeoDa develop data sets using a proprietary algorithm to kind of make them all compatible. But so if you have, for example, county data, I think they start in 1970. So from 1970 on, these county data are consistent, or the census tracts are consistent. However, if you go before 1970, you're out of luck. And so in some of the work that I've been doing, we're looking at the census tracts in Chicago. Before 1970, these do no longer line up with the ones from GeoDa. So then you have to basically, by hand, make sure that you have a set of units that remains constant over time. Because if that's not the case, then you're in an unbalanced panel situation. And so what's nice about a balanced panel, for example, a couple of things. The number of cross-sectional units is the same every time. And as an aside, the spatial weights matrix is the same every time, which really simplifies your life. In an unbalanced panel, and there's all kinds of degrees of unbalanced panel. So one example of an unbalanced panel would be having census tracts before 1970 and after 1970. They're basically the same things, but they don't completely align. So that's a little bit unbalanced, and with some work you can make it balanced, I should say, right? But then there's other situations, and I ran into this recently, is if you look at, say, a lot of house sales transactions over time. To have a balanced panel, you could only consider repeat sales of the same house over time, and in most markets there aren't enough repeat sales in a time period of interest. And so if you go back long enough in time, you get them, but say if you do quarterly house sales in an urban area, these tend not to be the same houses. They're still cross-sectional data sets, they're still cross-sectional in roughly the same space, but it is not exactly the same space. And so a couple of consequences. The n dimension is not constant. So, you stack up vectors of different length, basically, in the panel data set. These observations are not necessarily the same. So then you have to really think carefully how you construct the weights matrix. So is the weights matrix specific for each time period? So basically you create a new one for each, say, each quarter. Or does the weights matrix span over different time periods? And so then in a balanced panel, this is a non-issue, because it's the same cross-sectional units, is the same weights matrix each time period. In an unbalanced panel, you have to really think about it. For example, is a house, that sells in quarter one potentially correlated with its neighbor that sold the quarter before? Or is it only correlated with neighbors that sell in the same quarter? Right? So these are the kinds of things you have to think about in an unbalanced panel. So the bottom line is it's a lot harder to do. In practice, it means you probably have to write your own software, because there's nothing there out of the box to deal with that with the spatial weights. I mean, without spatial weights, yes, you can deal with it, but with the spatial weights, it's not that straightforward. So that's the first thing to think about, balanced versus unbalanced. The second one is what I alluded to, is the weights matrix, right? So we have data that are both over time as well as cross-sectionally. There's no such thing as a space-time distance metric, right? There is a distance, people can reasonably agree on a distance metric in a cross-section, the bandwidth, say in a kernel estimation, or commuting time or some reasonable distance to the nearest something or other. But then how does that work in space, in time? How does that work? Well, in time it works as well, because in time you know what is before what is after what, 2 periods before, 2 periods after. But then if you mix the two and you have, say, well, think about counties, right? If you have counties in 2 censuses, 10 years apart, right? And you have to build up a correlation system, space-time correlation between counties at the 2 different points in time and across space. So how far do you go to reasonably define neighbors that also are relevant 10 years later? And then there's no correct answer for that. It really depends on what it is you're modeling, what it is you're studying. The essence is if you don't have some theoretical sense of the speed of the dynamics, right? Because ultimately you're modeling a dynamic phenomenon. Think of diseases and disease spread, right? Is it relevant if you're looking at flu to look at things that are 10 years apart? No, by that time the flu is gone, right? There's no more correlation. But then other things may have to do, say, with infrastructure investment, new highways, high-speed rails that have long-term effects, and they, progress through time as well. So the typical approach, I mean, it's not the only approach, but it's the one that works the easiest, is to keep the weights constant over time. So you have this only works, as I mentioned, in a balanced panel. So in a balanced panel, you take the same weights matrix at each point in time, and you let the parameter change. If you recall at the very beginning, when we talked about the concept of spatial autocorrelation, it was really an interaction phenomenon. So it was really the product of the parameter with the weights matrix. And remember, I mentioned if the values in the weights matrix are larger, then the spatial coefficient will be smaller and vice versa, right? So now, if we let the interaction change over time, how are we going to model that? We either keep the coefficient fixed and let the weights be different, or we keep the weights fixed and let the coefficient be different. If we let both be different, then we can't tell what's going on anymore, right? If the weights and the coefficient are let to change over time, then we don't know which is which, because the interaction is really a combination of the two. So one of the two, to really figure out what's going on, one of the two has to be fixed. Now, it's easier to keep the weights fixed, although there is a literature that doesn't, let the weights vary, but then the coefficients have to be fixed. Yeah. So this is our first introduction of the Kronecker product. Just for those of you who are a little rusty on this, it's every element of the first matrix multiplied with the second matrix. So here, let's say we have 3 time periods. So IT is basically a 3x3 matrix with 1s on the diagonal. The zeros we don't have to worry about. So the first 1 gets multiplied by this big weights matrix. So that's a block of n by n weights. Then the second one, same thing, that's another block. And then there's a third block. So this becomes a big 3 by n by 3 by n matrix with 3 big blocks on the diagonal, but they're the same. They're the weights, right? So that's a straightforward way to write what is in essence a very complicated thing, a very big thing. This is a very concise way of writing this huge NT by NT matrix. And the thing we will exploit is the fact that only the diagonal elements, the block diagonal elements, have weights in them. Everything else is 0, so we won't have to worry about it, right? In other words, there is no spatial spillover between time periods. Very important, right? So the way this is constructed, there is no spatial spillover between time periods. And you may say, well, what about space-time dynamics? We get space-time dynamics through this concept of separability. And in essence, separability is dealing with each dimension in turn and then putting them together. So we deal with the cross-sectional dependence using a weights matrix. Then we deal with the time dependence using whatever structure we end up with. And then by putting them together like this, so this is a T by T covariance matrix for the time correlations and the potential difference in variance, the heteroscedasticity over time. That's T by T, which is the number of periods. In our example, typically this is very small. 2 periods, 5 periods, not very many periods. This one is very large. This is the n by n spatial variance covariance matrix. And it's the same principle as we've always seen. We get the structure of that matrix by assuming a spatial process, like an autoregressive process. So this sigma n will, typically encompass a spatial autoregressive structure or a moving average structure or something of that nature. This sigma t could incorporate a time series structure or a non-parametric time covariance measure or something like that. And so the space-time dynamic, how is location I at time t correlated with location j at time s? So different locations, different time periods, that comes from the combination of these two variances. So one is a time by time variance, one is a space by space variant. By putting them together, this is every element of the time correlation matrix, if you wish, is multiplied with this whole spatial correlation matrix. And so by putting them together, we get the space-time dynamics. So takeaway points is that spatial panel data are structured different from the textbook case. They're basically cross-sections stacked on top of each other, which will affect our notation later. We will work with balanced panels. Unbalanced panels can still be done, but they're much more complicated. The balanced panels allow us to keep a fixed, constant weight structure for each time period. And then finally, the space-time dynamics come from putting together the two separate entities. They are separability of the spatial dynamics and the time dynamics. Now, there are models that do not satisfy this separability. But then you have to have an explicit model for the space-time dynamics, which is much more difficult. So since we only have so many weeks in a quarter, I can't get into the dynamic panels. But in the dynamic panels, this is not necessarily the case, right? But in the static panels, we treat the cross-sectional dependence separate from the time dependence, and then we get the space-time effects by putting the two together. So what are some of the models? What are we interested in this? And we're really interested in the additional information that stacking together these two dimensions gives us. And we're interested, just like we were before, in heterogeneity and dependence. So cross-sectional heterogeneity, meaning there is some difference, typically unobserved, between the individuals in the cross-section, be it aggregate units or, say, houses or something like that. Or we can have temporal heterogeneity, that there is something that affects all cross-sectional units equally at different points in time. Often this is used to correct for inflation or business cycle effects. Like, so if the business cycle, which isn't true by the way, but often is assumed to work uniformly across the cross-section, then you could have a different time effect depending on where you are in the business cycle. And so then all the cross-sectional units at that time are affected equally. We can't really measure it, it's unobserved, but we should take it into account, right? And then, so with the cross-sectional heterogeneity, it's the same thing. It's something that is specific to the cross-sectional unit, but stays the same over time. You know, say in a labor market model, it's the education or the training, right? Or, you know, some initial assets that the units have. So each county has its own kind of distinct assets, amenities, and you can't really measure them, but you know they have them, and they don't change over time. So each county is different. There's this individual heterogeneity specific to each, but it doesn't change over time. So that's the way, you know, again, we have this orthogonality, right? We're going to think about heterogeneity across space, but doesn't change over time. Heterogeneity over time, but doesn't change across space. And of course, you can always generalize that and make everything heterogeneous over everything, but that's going to become much more difficult to track. So that's a typical approach, is to take each dimension separately and then put it together. And we can do the same about the dependence, as I already mentioned. And of course, this gives us all kinds of combinations, right? Do we consider individual heterogeneity and time dependence, or do we take cross-sectional dependence and time heterogeneity, or do we take all four? You know, there's lots of combination possible. Where this bites us is in potential identification problems. So when you put in other words, when you put fancy models together, make sure that you can still interpret the coefficients that come out of them, right? That you're not mixing heterogeneity with dependence to a point that you can't tell one from the other. Beware of multiplicative coefficients, right? If you have, you know, alpha times beta, then you can identify the product, but not alpha and beta separately. If you have alpha plus beta, same thing. So it creeps up on you. If you don't pay attention, you know, you write these really fancy models, but then write down the reduced form, and before you know it, you have these identification problems. And that's relevant if you want to separate out, for example, the spatial effect from the time effect. So an identification problem would typically give you a space-time effect that is identified. Think of a product, but it doesn't necessarily have the spatial and the time effect separately identified. And this whole separability idea is that you make sure that the spatial aspect and the time aspect are separately identified, and then you get space-time by putting the two together. So that's something to think about. Okay, so we've done this already in a cross-sectional sense, but now it becomes a little more complicated in that everything has an I-T index. I for the cross-section, T for the time. So the classic pooled setup, which is the easiest one to do, it's a straightforward generalization of the cross-sectional case, has a constant beta. So the Y varies between I and T, the X varies between I and T, beta is constant. The error term can be all kinds of things, right? Constant variance, not constant variance, correlated over space, correlated over time, and so on. So this model is basically too simplistic to be really useful, but I find it good as a benchmark. You know, before you start to get too fancy, you get a sense of what would the data tell you if you assume a very simple, stable model over time and across space. You know, what are these betas? And then you can start thinking about, well, let's vary the betas. And we've seen this before when we discussed spatial heterogeneity, that, you know, if you let everything vary, you're out of luck because you have this thing called the incidental parameter problem. And so this kind of setup is not operational in a classical paradigm, as I mentioned a couple times in passing. In a Bayesian paradigm, because everything has a distribution, you can actually have you can write out a model like this as long as you then have a distribution for the beta IT that is parsimonious in a small number of parameters, right? I mean, you can't have a different parameter for each observation as such. And the way the Bayesian paradigm gets around that, it says, well, we actually do have a different parameter, but that parameter has a distribution that, you know, the mean varies, for example, in function of characteristics of the location, and the correlation structure varies in function of different time periods. So that's how you put this space-time variability of the beta IT into the model. There isn't actually a separate beta IT estimated directly, but you get it indirectly because you come up with a distribution for beta IT, which has a limited number of parameters, and those parameters then dictate, in a sense, the variability of the beta across space and over time. But this, as such, doesn't work. So you cannot have a number of parameters that increases with the sample size. So what we're going to do is impose structure and let these parameters change in a particular way. So the classic textbook approach for panel data econometrics, and the classic text is by Badi Baltaji, and if you want to do any kind of panel data analysis, you have to work through that book. So the classic approach is to focus on individual heterogeneity and time dependence. So that's kind of the, I mean, you can have all kinds of combinations, but if you look at the literature, the empirical literature, this is typically how it's set up, you know. So the spatial approach obviously focuses on spatial autocorrelation, spatial cross-sectional dependence, and the temporal heterogeneity is actually very easy to deal with, as I'll show you in a few minutes, because typically there aren't very many time periods. So when there aren't very many time periods, you can easily deal with them as fixed effects. You know, when you have situations, and there is a literature that has these situations, where N and T are more in balance, then it gets more complicated, right? And the basic way to approach this in the literature is to think of this heterogeneity and also the dependence to some extent as either a fixed effect and a random effect, or as a random effect. And the irony of it is that mathematically they look exactly the same, but substantively they're very, very different. The fixed effect is something that doesn't scale with the dimension of the effect. So for example, if you have individual heterogeneity with a fixed effect, which gives you a separate intercept for each cross-sectional unit. So let's say each county has its own intercept. So you have 3,085 intercepts, okay? Well, nobody in their right mind is actually going to estimate 3,085 intercepts, but they are going to wash them out, as I mentioned, by demeaning, by taking the difference between the observation and the average over time, and the average over time of a fixed effect is 1, right? The fixed effect is a constant over time. And so the difference between 1 and the average over time, 1, is 0, so it's gone, right? So that's how you deal with fixed effects. There is another interpretation of spatial fixed effects, and this is a little bit confusing. So the classic panel data interpretation of spatial fixed effects is that every cross-sectional unit, every I, has its own intercept. A slightly different, more of a multi-level interpretation of, or implementation, I should say, of spatial fixed effect is that there is a different intercept for each larger entity. So for example, you would have counties again, but all the counties in the same state would have a fixed effect. That's kind of more of a multi-level thinking. And this is used quite a bit in the literature, and I may have mentioned this before. It's often argued to be a way to correct for spatial autocorrelation. Sometimes it does, sometimes it doesn't. In general, it does not. It does correct for spatial heterogeneity to the extent that all the counties in the same state have kind of a state effect, and that state effect remains the same over time. So that's a little bit different twist on this. So now we get fancy, right? How do you write this concisely? And this, it's essential that you get a good grasp of this, because all these vectors and matrices have different dimensions. And I try, whenever there's confusion, I add a dimension to them. So think of what this really is, right? This is a stacking. We have one cross-section. So in this cross-section, each element has its own fixed effect. Then we have the second cross-section. Each element has the same fixed effect as before. So how do we write this? This is the vector of all the fixed effects that we just stack over time, right? And using the Kronecker notation, we have IT, or iota t, which is a vector of ones, a vector, not a matrix, of ones of dimension t, the time dimension. So if we have 3 time periods, that's 3 ones. And each of these ones, it's a column, it's not an identity matrix, it's a column. Each of these ones gets multiplied with this vector of all the cross-sectional effects. So what this does is the first one takes the cross-sectional effects, then the second one takes them again, and the third one takes them again. So in fact, the stacking of the same cross-sectional effects for each time period is concisely written as the Kronecker product of a vector of ones of dimension of the time dimension, Kronecker with a vector of dimension n for all the cross-sectional fixed effects, and the rest is standard. Right. So here the fixed effects are actually coefficients in the model that can be estimated. The main substantive implication of this is that these individual fixed effects can be correlated with the other variables in the model, because they're basically like another variable. So if you have, say, a state culture effect or a country legal system effect that you have very hard time quantifying, say, in an international relations model, right? So that effect could be correlated with GDP or with energy production or something else, because it's just treated as a constant. In contrast, if that effect is viewed as random, it becomes part of the error term, and we know, or should know by now, that the error term cannot be correlated with the other explanatory variables. So if you do the random effects, you have to be pretty sure that whatever that effect is not correlated. For example, in my international example, that the legal system effect is not correlated with GDP or with education level or with infrastructure or something like that. And there's a classic test for that, which I won't talk about here because there's nothing spatial about it, which is a Hausman test, which is basically can you tell the difference between a fixed effect and a random effect in the sense that if there is correlation between the between the effect and the other variables, you should be able to tell. And that's what this test is based on. So cross-sectional heterogeneity, that's actually the classic focus in panel data. But it's also interesting to think about temporal heterogeneity, because this is very easy to do. As I mentioned, unlike the cross-sectional case, where you would end up estimating 3,085 intercepts with, 4 maybe 4 time periods to estimate them from. Here, it's the other way around, right? So we only have very few time intercepts, but we have lots of observations for each cross-section to estimate them from, right? So this is actually my preferred approach in dealing with spatial panel data, is to deal with the time heterogeneity explicitly as a fixed effect, okay, not as a random effect. It solves a bunch of problems. I mean, first of all, the time series dimension tends to be short, so you don't have the asymptotics that you need for the random effects in the time dimension, so that takes care of that one. And there is typically enough information in each cross-section to get a pretty decent, pretty precise estimate for the time intercept effect. So basically, what this intercept effect measures is how the dependent variable would be different if everything else was the same. It would be different between time periods. So it's not different because aspects of the right-hand side change. So it's not different because the GDP changes or the education level changes. That's built into the model. But it changes because of unobserved time heterogeneity, things that we somehow are not capturing in the model, you know, say some political sense in the country that we don't have in the model, and it can be correlated with the other effects. We don't care about that. We have it in there as a constant term, as an intercept. So then this heterogeneity over time, controlling for everything else, is taken into account. And why would you do that? Because if you don't take it into account, then the other parameters will pick it up. Just like as we've seen in the spatial lag model, if you don't put a spatial lag term in there, the other parameters will pick it up. And in that sense, they will be biased, okay? So this is a little bit different here. How do we write this in our fancy Kronecker notation? So we have a cross-section for each time period. So the first cross-section has the first fixed effect, the same one for the whole cross-section. The second cross-section has the fixed effect for the other time period. So here we have a t vector, a short one, with the individual time effects, Kroneckered with a vector of n ones. So the first time period, we have its effect time n ones. Second time period, its effect time n ones. So this is the way we, again, write very concisely how all this stacking is going on, right? So you got to see these Kroneckers in your head, because pretty soon we're going to be multiplying them together and doing inverses and all that fun stuff, and it gets complicated. So then the random effects, classic model is basically, you know, the same setup where we have an, if you wish, an individual specific something, coefficient, but now this coefficient is not seen as separately estimated, but is put in the error term. So we now have a composite error term that has two parts. One part is the unobserved individual heterogeneity. So that is constant over time, but different for each individual. And rather than saying we're going to estimate them individually, we make them part of a distribution. And this sounds a little bit like the Bayesian way, right? So we say this effect, this individual heterogeneity effect, is normally distributed with a mean of 0 and with a variance of sigma squared mu. Okay? So what this does is it corrects the estimation of beta for the presence of the individual heterogeneity, but it doesn't and can't give us an estimate of the unit-specific individual heterogeneity because it's part of this distribution. I mean, at best, what we could do is start, sampling from that distribution and having an idea of what that heterogeneity might be, but that's very different from estimating a county-specific intercept, for example. It's a totally different way of thinking of it. And the reason this has so much attraction in the literature is because at the end of the day, all we care about is beta. Okay. So in the spatial world, that's okay, but I'm personally much more interested in figuring out what these location-specific individual effects might be. So from that perspective, a fixed effect rationale is more attractive than a random effect rationale. There's a catch, however, because the fixed effects is a different intercept for each cross-sectional unit. So if we need the number of cross-sectional units to go to infinity, which we typically do in the spatial arena, we're in trouble. We have an incidental parameter problem. And that's a big deal because in essence it's telling us no matter what you do, you cannot estimate these individual intercepts consistently. You can get an estimate, but that estimate is not that good, right? And so then we're out to lunch because we were really interested in these individual specific effects, but at the end of the day, we can't really estimate them consistently. So at the end of the day, it does make a difference because your focus, if n goes to infinity, has to be on beta. These other things, the individual heterogeneity, is just there to get a better beta. It's not there to actually estimate the individual effects as much as you would like to. But of course, if you have an estimate of the variance of mu relative to the variance of the remainder error term, then you get a sense of how much this heterogeneity matters, right? If the variance of mu is teeny compared to the other error variance, it's not going to matter very much. If they're somewhat balanced, then there is a lot of individual heterogeneity, and the fact that you account for it gives you better beta. That's the bottom line. So here's our next Kronecker challenge. So how do you get this one? Mu is a random vector of n elements, right? And so the Kronecker part is a short vector of ones equal to the dimension of the time series. And each of these ones is multiplied by an n by n identity matrix. So what you end up with is an n by n identity matrix on top of another n by n identity matrix on top of another one, as many as there are time periods. So then this identity matrix gets multiplied by an n by 1 vector of random errors. So it's n by n, so it's really nt by n. This part is nt by n. This is n by 1. So the product of nt by n with n by 1 is nt by 1. So we have a random vector for each observation out of this. Okay. And then the other one is nt by 1 by construction. That's the individual error. So each of these different specifications, they basically boil down to the same thing. We have the stacking of each cross-section on top of each other. How do we write that concisely if we have individual heterogeneity, which gives us n different either intercepts or n different random coefficients? Of course, the difference is going to be the intercepts actually need to be estimated in some way. The random coefficients do not. What we estimate for those is the characteristics of the distribution that generates them. And typically, that's assumed to be a normal distribution that's uncorrelated. And later next week we'll see cases where they're actually correlated. But these are characteristics of the distribution. They're not the individual specific effects. So then in the temporal domain, you can do the same thing. I'm not going to dwell on this. The one thing to realize is that the temporal random effects creates a cross-sectional correlation of a very particular kind, namely it's constant. So think about all the correlations, all the cross-sectional elements in the same time period share the same time random effect. So if you take their correlations, then the expected value of the product of these two time effects is the same time effect, is the variance of that time effect. So all the cross-sectional units, if you incorporate the time effect as a random in the error term, become cross-sectionally correlated of a very particular kind. And this is not necessarily what you want. So if you then also build in spatial autocorrelation in the model itself, you get a mixture. You get a mixture of the correlation that comes from the time random effect and whatever autocorrelation you build in to the model itself. So that creates identification problems. So that's why very often the preferred approach, at least I should say my preferred approach, is to put time heterogeneity as a fixed effect and cross-sectional heterogeneity as a random effect. Okay. So now the asymptotics, I already alluded to that. It's really complicated, right? Which of these goes to the limit? And depending on which one goes to the limit, you have problems for fixed effects for the specific type of effect in question. So with the cross-sectional dimension going to the limit, we have individual heterogeneity in the form of fixed effects gets you in trouble. If the t dimension goes to the limit, we have the same thing with individual time effects. So the typical setup, by no means the only one, but the typical one in a spatial panel is that t is considered to be fixed. So then you can easily have fixed effects for the time dimension, and then the cross-sectional dimension is the one that goes to the limit. Now, there's one problem with this, right? If you have fixed effects for the time dimension and you want to do space-time forecasting, what is your fixed effect for next year? You don't have it, right? So this doesn't work. If you want to use this for space-time forecasting, you cannot have a fixed effect for time. You need to deal with it in some other fashion. And either you deal with it as a random effect, or you deal with that through time-wise correlation in the error term, which you can then use for prediction, or you deal with it through an explicit dynamic model, a dynamic panel that includes these different effects. So typically, the easy solutions are, one is fixed, the other one goes to the limit. So t is fixed, n goes to the limit, or n is fixed, t goes to the limit. When they both go to the limit, then typically the theoretical work is concerned with the relative speeds. So how does, t grow relative to n or n grow relative to t? So for example, if you have, a large cross-section and you have a much shorter time series, then is the cross-sectional expansion dominant over the time series one, or is it the other way around? And that's primarily of interest for theoretical derivations, but it's something to think about, when you think about what is the point of your model, right? Are you interested in forecasting? Are you interested in finding structural relationships? That's not the same thing. So a model that's good for forecasting might not be good for structural relationships. So typically, if we have small n and large t, we model the cross-sectional covariance in a non-parametric way. That is the classic, seemingly unrelated regression model or vector autoregressive models from time series, and no t fixed effects in that one. And if we have small t and large n, it's the other way around. We use the spatial asymptotics. We use models for spatial dependence, parametric models. And then we can have a non-parametric estimate of the serial covariance. Right? And we get the incidental parameter for the individual fixed effects. And then large n and large t, anything goes. Right? So a little bit about dynamic panels, mostly to give you a sense of how complicated this is. Okay. So I have developed over time, well, actually a long time ago, a taxonomy. In some of the more recent papers, there's a slightly different terminology that used, but you'll get the gist. Okay. So the first one, the essence is that you have spatial effects. You have neighbors, but the neighbors are in the previous period. So this model lends itself very well to modeling spatial diffusion, the spreading of phenomena. You have, basically you explain a phenomena in a given period at a given location by that phenomenon in the neighboring locations in the previous time period. So if you're looking at, say, adoption of new laws or new regulations, or there's a literature in environmental modeling, how different environmental regulations get adopted by states. Some states are way ahead of the game, like California, and others are laggards, like Texas, but how does that actually spread through the system? And, you can look at ideas, you can look at the adoption of new technologies, things like that, right? The problem with this, and there's two big issues with these kind of models. One is to figure out what is endogenous and what is not, right? And so endogeneity is one, the variable is correlated with the error terms. So if you look at this, and I'm not going to repeat this for each model, but just give you a handle on how to think about this. So here's yt minus 1, right? So yt minus 1 includes the error term at t minus 1. Right? So we have to make sure that whatever is in yt minus 1 is not correlated with the error term at t. So this will be the case as long as the error term at t is not correlated with the error term at t minus 1. Because then there's no problem, right? The only randomness in the y, it comes from the error term in the previous period. If these two error terms are not correlated, we're in business. We can treat this as an exogenous variable. Anything, you don't need anything special. It's just OLS and you're done, right? However, and often that's a tough assumption to make. A more natural assumption is that there is some inertia in the unobserved effects in the error term, so then you would have correlation between the error terms at different points in time, and then you have to instrument. And that's the classic in panel data, in dynamic panels, you have to think about instruments, generalized methods of moments, and all that kind of stuff, right? Inertia is just if there's serial correlation. So you can think of the error terms as the non-systematic ignored effects, right? If they're systematic, they should be in the model. They're non-systematic. These are things that on average are 0. Otherwise, they wouldn't be error terms. But if you have let's say this has to do with the political climate. So the political climate, you can't model it, it's in the error term. Or entrepreneurship, okay? Great term, conceptual, how are you going to measure it, right? So some of that has to be in the error term. So the entrepreneurship doesn't really change that much from year to year, which means that these error terms will tend to be correlated from year to year. And then whatever is the, the neighbors at the previous point in time will be correlated with the error at the current point in time through the correlation of the error terms over time. So that's the key thing to keep in mind in terms of endogeneity. The other thing to keep in mind is identification. So what are the coefficients that we have in here? And so one thing you often see is that in addition to yt minus 1, xt minus 1 is included as well, right? But xt minus 1 is already in yt minus 1. So then you have to be really careful and really build the reduced form to tease out what is the true effect of xt minus 1, because you have it in there twice. You have it in there through yt minus 1, and then if you add it explicitly, then you have it in there a second time. So the coefficient of xt minus 1, the beta, is actually not the full effect of xt minus 1, because there's also some effect in this gamma coefficient from the previous time. So this is the other thing that gets very tricky in these models. So, you should know me by now, simplicity really pays off. And so start with a simple model, see if it's good enough. If it fails in some respect, then maybe start adding these other aspects. But each time, the two things that bite you are endogeneity and identification. So endogeneity has to do with whether these new variables that you introduce remain uncorrelated with the error term, and identification means whether the coefficient of whatever variable you have included in here measures the total effect of that variable, or in fact there is already some effect of that variable through other coefficients, and then you have to tease them out. So this is the easy one. Then in this one, everything is lagged. So we have a lagged same period as well as a lagged neighbors, and some people would argue this is the best measure of space-time dynamics. So it's not just the neighbors in the previous time, but it's also whatever the inertia is or the serial correlation in this place itself. So, the tax rate in a state at a given time are a function of both the tax rate in that state in a previous period as well as the tax rates in the neighboring states in the previous period. And then you can tease these apart, and this is very useful for a space-time forecasting model. Again, you have to worry about serial or spatial dependence to make sure that these are exogenous. Otherwise, you have to use instruments, and then you also have problems if you have xt minus 1 in here. That's the identification thing. This is a different twist on this. It uses the lagged dependent variable in time, but then the neighbors contemporaneously. So this is the tax rates in a state are a function of the tax rates in the previous time period in that state, but the current tax rates in the neighbors. Is this useful? Maybe, maybe not. I've seen it. So that's why this is a taxonomy, right? This is about all the different combinations that you can have and that are somewhat meaningful. You can get a space-time multiplier from here, but again, you have to watch out if you put in spatially lagged explanatory variables with identification problems of the coefficients. And then this is everything, but this is actually not a very good model because it has all the problems that you can dream of. It has endogeneity, it has identification problems, but it has everything, right? Dependence in the same period, dependence with the neighbors in the dependence in the same location previous period, neighboring locations previous period, current neighbors, right? All of it. And so this one is a little complicated. But this is just to give you a taste of how much more complicated dynamic panels are relative to static panels. And just to give you a quick overview, pooled panels are easy. You basically stacking everything and treating it as if it was a single regression. And it's easy as can be. The spatial models, again, we have some notation, and I introduced that here because next week it gets much more complicated. So this is a spatial lag, pooled spatial lag, with the same autoregressive coefficient in each time period. So basically, you can think of this as a spatial lag model for each cross-section. And you have different cross-sections, but you're forcing the autoregressive coefficient to be the same in all time periods, just like you force the betas to be the same in all time periods. And a slight twist on this is to introduce time-fixed effects. So then you deal with time-wise heterogeneity, but you have the dependence through the spatial lag model. And again, this should be familiar by now. This is the same structure as before. We have the time periods, and each time period gets a block weight. And it's the same weight in each time period, in all the time periods, right? So then spatial error model is just a little bit more complicated because now we have to put the same structure but dealing with this complex variance covariance matrix. So we rewrite the error term in its reduced form, which gives us this nice inverses. And so then we see that for each block T, we have this cross-sectional variance covariance matrix. But as we've already seen, you know, that's just for each block T. Off diagonal, there's nothing. So we get, again, a block diagonal matrix with these big n by n blocks, which take this form. So same thing here, constant variance, not very realistic. Our little T identity matrix, and each element has this big block, this nasty inverse matrix that we've already seen before in the error models. So again, from a practical point of view, this is nothing but a huge cross-sectional estimation where now the variance matrix has this block structure, but what's good about this is that it's the same block structure. So you don't actually have to do T different variance matrices. It's the same variance matrix T times. So that simplifies things greatly. And then the Lagrange multiplier tests are just easily generalized in these pooled models. You know, it's all the same thing except that you have this capital T in there, which basically says we do everything T times. That's what it boils down to. Because there is not, as opposed to what we'll see next week when we deal with seemingly unrelated regressions, is the same parameter in all time periods. When we have a SIR model, it's a different parameter in each time period. So then the tests are a little more complicated because they have to allow for that variability. Just to give you a sense of what this looks like in the few minutes that remain, just some examples of how you can do this in GeoDa and GeoDa space. So this is a very simple pooled model. Basically, the way you go about this, and this is spelled out in detail in the two notes, is you use the time editor in GeoDa. So the time editor in GeoDa allows you to group variables. So if you think of my example, always the same one with the homicides, so you have homicides in 60, 70, 80, 90. In the time editor, you group these so that it knows these are the same variable at different points in time. So then the variable comes in with a single term. You do this for all the variables, and then there's a little button that says Save Spacetime Dataset. And that, in essence, stacks all these things on top of each other and make them one panel data set. And at the same time, it takes the weights matrix and, in essence, stacks them on top of each other and creates this block diagonal structure as a sparse GAL file. And then with that data structure and the sparse GAL file, you're in business and you can do just the standard commands. In GeoDa, you specify a regular model and you get the diagnostics for spatial effects, because GeoDa doesn't know this is a panel model. That's the beauty of it, right? As long as the data are stacked properly, that's all that matters. And then you can do a lag model. Here's a pooled lag model using maximum likelihood. You can do the same with spatial two-stage least squares, but there's a catch. Okay, just to see if you're still awake, what is the catch? If you look at what is going on, I'll give you a hint. Focus on the instruments. Something's missing. Remember, spatial lag. What are the instruments? They're the lags of the explanatory variables. The explanatory variables are given all here. The time is not there. Because remember the other day when I was talking about the spatial lags of the explanatory variables, one you get in trouble is when you have time dummies. This is when you get in trouble. So if you read the little document that I prepared, then you will see that if you do the standard spatial lag, spatial two-stage least squares, it blows up. It blows up because it creates the spatial lags of the time dummies, and that creates near multicollinearity, and you have some really interesting results that are wrong, right? So what you have to do then instead, and it's very easy to do in GeoDa space as well as in GeoDa, is you create the spatial lags explicitly. So these variables, this is actually, if you look carefully, this doesn't say spatial two-stage least squares, right? It says two-stage least squares. Why? Because I have created these spatial lags explicitly as new variables and then put them in the instrument box when I estimate the spatial lag model. And this is how you get around the time dummy trap, so to speak. Right? And then you can do the same with the error models. Maximum likelihood, no big deal. It gives you the pooled results as well as spatially weighted least squares using the heterogeneity. This is what we saw the other day. This allows for unspecified heterogeneity. So these are all the basic models. This is all very easy to do. What are the flaws? The flaws are that heterogeneity is not taken into account. None. I mean, a little bit with the time dummies, but no cross-sectional heterogeneity is taken into account at all. And no potential heteroscedasticity, where the variance is not constant over time periods, that's also not taken into account. So what we're going to do next week is to tackle these complications and explicitly incorporate individual heterogeneity in the form of fixed and random effects first, and then incorporate, if you wish, extreme heterogeneity where every time period has a different set of parameters, which then allows us to test for homogeneity of the parameters over time. And in an ideal world, if you test for homogeneity of the parameters and it says, yes, they are, then you go back to this, because this is exactly what that allows. One slight advantage of using these approaches, the GMM and the instrumental variables approaches, is that you can deal with heteroscedasticity using the white variance specification. So that just works like in the same simple cross-section. The maximum likelihood, as we already know, doesn't know how to do that. So that would be an advantage. So you can deal with a little bit of temporal heterogeneity using the standard pooled I mean, there's nothing pooled about it. The standard estimation routines from GeoDa space, but you cannot deal with kind of the classic panel features, which is unobserved individual heterogeneity, fixed or random effects, or, you know, complete heterogeneity in the SIR sense. So that's what we'll do next week.